In this video, I'll work through an example in which we adjust some constants in order to make a piecewise defined function continuous. Consider the function defined in pieces as follows, where a and b are unknown constants. If x is less than -2, f of x is defined as a times x squared. If x is between -2 and 1, including those endpoints, f of x is defined as the sum of a linear function bx and a square root function. And if x is bigger than 1, then f of x is defined as this linear function with slope a. Our challenge is to find values of a and b that will make this function f continuous. The points we need to worry about are the places where the rule changes. So we need to worry about when x equals -2 and when x equals 1 because we have potential jump discontinuities there. We might also be a little bit concerned about this square root function and the x value of -3, since the square root function fails to be continuous when x is less than -3. However, that's not really a problem because this rule only applies when x is between -2 and 1. So let's worry about x equals -2 first. At x equals -2, for f of x to be continuous there, we need for the limit as x goes to -2 of f of x to exist and equal f of -2. For the limit to exist, we need the limit as x goes to -2 from the left to equal the limit as x goes to -2 from the right. Now, the limit as x goes to -2 from the left, to evaluate that limit, we're going to need to use the first rule, Rule 1. Since x values coming in from -2 to -2 from the left means that x is less than -2. So let me copy down that rule. That's ax squared, and we can evaluate that limit just by plugging in -2 for x. A times -2 squared, which is 4a. On the other hand, if we're evaluating the limit as x goes to -2 from the right, then that means that x values are slightly bigger than -2, so we need to use Rule 2. That is, we need to evaluate the limit as x goes to -2 from the right of bx plus the square root of x plus 3. Again, we can evaluate that limit just by plugging in -2. That simplifies to -2b plus 1. So we need those two limits to be equal to each other, 4a to equal -2b plus 1, and we need both of those limits to equal the value of f at -2, but the value at f at -2 is just what we get by plugging in -2 to Rule 2, so that's just the -2b plus 1 that we got when we evaluated the right-hand limit. Now we have one equation relating a and b, but we need one more equation to be able to solve for these two variables. And we can get that extra equation by looking at x equals 1, the transition point between Rule 2 and Rule 3. At x equals 1, we need the limit as x goes to 1 from the left of f of x to equal the limit as x goes to 1 from the right of f of x, and those to equal the value, f of 1. Well, to evaluate the limit as x goes to 1 from the left, we need to use Rule 2. That's the limit as x goes to 1 from the left of bx plus the square root of x plus 3. We're using Rule 2 because we're evaluating 1 from the left through x values slightly less than 1. Once again, we can evaluate the limit by plugging in and getting b times 1 plus the square root of 1 plus 3, that's 2 plus b. To evaluate the limit as x goes to 1 from the right, we need to use Rule 3 in the piecewise definition. So that's the limit as x goes to 1 from the right of 4 plus ax, evaluating by plugging in, we get 4 plus a. Now we need to set those two limits equal to each other. So we get 2 plus b equals 4 plus a. The left-hand limit has to equal the right-hand limit, which also has to equal the value. But the value, again, we're getting just by plugging in 1 into rule 2, so that was already the 2 plus b that we got from the limit on the left. Okay, so now we have two equations and two unknowns, so that should be enough to solve. I'm going to solve by isolating a in that second equation. So a is going to be 2 plus b minus 4. In other words, a is b minus 2. I'm going to plug that in to the other equation. So that means that instead of 4a equals negative 2b plus 1, by plugging in a, I'm going to get 4 times b minus 2 equals negative 2b plus 1. If I distribute, 4b minus 8 equals negative 2b plus 1, which gives me, if I move the b's to the left and the constants to the right, I'm going to get 6b equals 9, which means that b is 9/6 or 3/2. Plugging that value of b back into this equation, that gives me a is 3/2 minus 2, which is negative 1/2. So I have a equals negative 1/2, b equals 3/2 as the special values of the constants that will make my original piecewise defined function continuous. In this video, we figured out the constants that would make a piecewise defined function continuous. I've graphed the piecewise defined function in Desmos. The first piece, with the x squared, is drawn here in red. The second piece, with a square root in it, is drawn in green. And the third piece, this linear piece, is drawn in purple. If I adjust the constants to get a to be negative 1/2 and b to be 3/2, 1.5, you can see that the pieces line up to make the function continuous.